Hello, so in the video today I'll explain a little bit more about how we can do modeling of veins. For this I'm using a fairly simple to show the workflow in fairly simple case, and then we'll create another video at some stage where we do a more complicated one where you have branching veins, but the principle will be roughly the same for those ones anyway. So instead of just extracting inside-outside points directly, when you have very thin structures, that won't always work. So here the quartz porphyry zone is actually not very thin. We probably could just extract the indicator points directly here, but for demonstration purposes what we'll do is actually extract hang wall, footwall functions first, and then use those in a descriptor. So for this, I've actually created a selection already. So on this data, so here we have two selections. One is the quartz porphyry more for the tops, and one for called the bottom, where we wanted to have the lower part of this vein structure. Some things to notice in this selection, I won't go into that today, but if you look at the quartz porphyry, I didn't select any of the intervals here because the intervals actually connect all the way to the topography. If you extract contact points there, you get points at the topography, and it will try to curve around the structure, and it's not really recommended. So I've only selected those parts which are below the topography, so the purple sections here. Similarly for the other, for the bottom section, I didn't include any of the drill holes that didn't continue downwards, so they stop here at this level, but clearly the quartz porphyry extends outwards. So if I would select these ones, I'd create a number of contact points here that I don't want. Alright, so with these two selections, let me just hide them again. Okay, just hide all. Alright, so now we go to processing here. So we take our drill data, and in this case we go to the surface-based modeling. So here we extract the contact points, which is more of a surface-based method, but we can use it for these situations as well. I'll demonstrate what it does. So we use our manually selected segments here. So we'll start with the bottom selection. So of this selection, we can select if we want to have the start of each interval that we've selected or the end. So we want to have the end parts because we do the bottom half. Alright, so let's do bottom points here. Let's run this one. You can see we've got a number of contact points now that we can use. In surface-based modeling, you'd probably create a surface from that, and then use that in your modeling. But in this case, that's not what we want to do. We want to do volumetric modeling. So we want to get to classification, but we don't have any inside-outside points at this stage. What we can do is we can use this offsurface indicator points method directly on these points here. So what this does is actually it takes the input points, just give it a name, bottom, and it converts it into indicator points. So it creates an inside-outside point at a certain offset from those points. I'll use 2 meters. The number of orienting points is important to know what side will be the inside and what side would be the outside. Very curved structures, you probably want to reduce the number. If they're very planar, very flat, for example, you might increase it a bit further. I'll leave it at the default for now. So what it does now, if you look at this, so now you have two sets of points, at least. Maybe turn these off. So you have your red points, the inside points, and your outside. Notice that for these sort of structures, the inside-outside can be a bit arbitrary. So it just estimates one side versus the other side. So in some cases you might have to turn it around, and then there's this option here to invert the orientation. But for now, I'm happy with this. So now I've converted my contacts into off-surface points, and I can actually use a classification on this now. That's what I'll do next, and say, okay, this is my bottom function. Notice that we can have an automated anisotropy estimate here, so I'll do that fast, although it tends to overcompensate at times. It's not bad in this case. It's already quite accurate. It seems to miss things here a little bit, so let's go to the function to increase the resolution just to see if it's actually missing them. Still a little bit, so I'd like to go to the anisotropy that it just created here. You can see that the strength might be a little bit too much in one direction, so I'll reduce that a little bit, and then make sure on the processing we turn off the estimated anisotropy. Just want to use the one that we just estimated and rerun it. Alright, so that already looks better. There's a bit of an area here where it doesn't quite honor it as carefully, so I want to reduce this maybe a bit to 60. Yes, this is a lot better. You can see that it's now only showing red on one end, one side, and blue on the other, so this is quite nice. I'm happy with this one. Similarly, we can do the same process, but then for the top one. So instead of using the bottom one, we use the other one, the other side, the other selection, and we want to have the starting intervals of that selection. Okay, so I'll just have to call this top, just to make it clear, and here we call this a top function. So we don't have to set the anisotropy anymore, because we assume that that's going to be the same for the bottom and the top. And you can see that we get a pretty neat function boundary there. Alright, so now how do we use this in our modeling? So let me turn off the top one again and turn these points off. So now we can go here and we create a new one. So I'll call this the vein that we want to model. And first we want to have the bottom function here, and we'll give it a new name which we call vein. Alright, so I'll demonstrate what this does first. Yeah, I want to turn off this topo because I want to see the full output. I'll just run this one for a bit. Okay, so now we have the first step in our model, and you can see we have something called a vein and everything outside. So everything on the right side, on the north side roughly, is unknown, and everything on the other side above the bottom function is actually vein, which is good. This is actually what we want. So at the moment it's just extending way too far for the vein, and that's where the second function comes in. So now we need to add the top function that we've created, so top function here, but we don't want to override the unknown, so we want to apply this to the vein because that's where we want to do the modeling. Likewise, we don't want to call this top or anything, but because we already have a vein part, we actually want to remove part of the vein that's actually not part of, that's actually no vein. So we want to relabel this back to unknown. And let's see what that does. So you can see that in the first step we created the domain called vein. In the second step we want to remove part of that domain by reverting it back to the default unknown. So I'll just run this one again so we can see what it does and if it's actually the result that we want. Alright, I've paused it for a bit and it's just finished processing. There you go. In this case it's already done exactly what I wanted to do. So if we look at this now, so we have now two units within this model. Part called unknown, which is everything outside of the vein that we've just modeled, and the vein itself, which is exactly the part that we wanted to model here. So now we can start using this vein for doing it for numerical analysis, for example. So I'm happy with this. And then I can go to the processing, remove everything, and I'll use only the visible data. So this vein model, I'll just use this actual vein section that we've just created. And here I can now evaluate this with a function or multiple functions. So let's use the copper estimation using machine learning regression, and we'll use the RBF evaluation as well. I'll give it a name, eval. And now we run this one. Now we have our vein with RBF copper estimates evaluated on it. So we can then go in here and say, okay, what's the estimated value above 1 gram per ton? So we can go back to the info tab to get our estimate and the volume. If at this stage you'd prefer to actually have a grade shell at a particular cutoff, you can do that as well, of course. So we'll wipe this. We can use all data or visible data. So I'll use the eval here, and then in modeling, surface-based modeling, we can actually extract a shell here. We can go here and call this a shell. So we don't want to have the shell from domains, but let's say we use the RBF for this at 1 gram per ton. We want to set this close the shell at the boundaries, so actually get a volume out of it. And now we can go back and you can see that we have a shell around 1 gram per ton estimation that we've done. So, and that concludes this video on vein modeling.